All right, when we left off, we were at this point where we have a recurrence relation, and we've defined this function f of r to recover the index equation. And we should note that if we consider f of r plus n, that we could replace all of this up here with f of r plus n. And so that's the version of the recursion that we're going to end up working with. So the end of our setup for finding the general theorem for Frobenius series is we are going to start with a function f of r is equal to r times r minus 1 plus p naught r plus q naught. And the recurrence relation can be written in the form f of r plus n a n is equal to minus the sum from k equals 0 to n minus 1 pn minus k, k plus r, plus qn minus k, ak. The temptation is that we would like to divide both sides by f of r plus n, but that's not something we're allowed to do because we don't know that that's equal to 0 or not. And in the case where we're looking at solutions of the indicial equation, then f of r is equal to 0. So we're going to leave it in this setup for now, and then we'll show when we can divide by f of r and when we can't. From here, we're going to consider three different cases of solutions to the same equation. We have, remember, r times r minus 1 plus p naught r plus q naught is equal to 0. Three things could happen in the solutions to this quadratic equation. The first is that we could have r1 and r2 distinct and real. Case 2, we could have r1 and r2 are real but coincident. That means that we have a double root. And the third case is r1 and r2 are complex conjugates. We know that if they're complex, they have to be complex conjugates because the coefficients to the equation that defined them are real coefficients. If r1 and r2 are distinct and real, we're going to make the assumption that r1 is greater than r2. In fact, even if they're coincident, we can always write r1 greater than or equal to r2 so that we can be consistent about that. So in either one of these cases, we're going to consider r1 to be the larger of the two roots. And there's a reason for that, because we're going to make an observation about f of r plus n. For case 1 and 2, assume that r1 is greater than or equal to r2. What that's going to mean is that the only two values where f is equal to 0 are r1 and r2. Those are the only two solutions to f of r is equal to 0. So if r1 is the larger of the two roots, then it must be the case that f of r1 plus n is not equal to 0 for any integer n. What that means is, as long as we know we've got one root, in all cases, we know that f of r1 plus n cannot be equal to 0 for any of the three cases. After all, an integer f of a complex number is not going to be equal to 0, and so adding an integer to a complex number is not suddenly going to make it into something that lets that polynomial be equal to 0. So that's the justification that we need to turn the recurrence relation into one that looks like the one we're used to. So with that, since we know now that that's not equal to 0, we can say that f of r1 plus n, an, is equal to this sum of previous coefficients, that in this case, because this can't be equal to 0, I can divide by it. And that's going to allow me to write an is equal to minus 1 over f of r1 plus n, sum from k equals 0 to n minus 1, pn minus k, k plus r1 plus qn minus k. So that means that we can always figure out the rest of the ANs if we know the AKs. In particular, what that means is that we're going to have, so what do I mean by that? If I wanted to know, it's illustrative to see what's going on with a recurrence like this, to see a couple of examples written out. So let's just suppose we've got R1 and we want to find the Frobenius series. And this is the recursion that we want to find AN in terms of A naught. I can do that because as I put different powers of n in, all that happens here is I make this number bigger and bigger. So for example, if you plugged in n equals 1, what you get is A1 is equal to minus 1 over f of R1 plus 1 times the sum from k equals 0 to 1, 0 to 0, of P1 minus k, k plus R1 plus Q1 minus k, ak. And that means that we get A1 is equal to minus 1 f R1 plus 1 times, well, what does this sum inside turn into? You get P1 R1 plus Q1 A naught. And so A1 is entirely in terms of A naught. When you put in A2, what's going to happen is you're going to get an expression that has a lot of junk running around. But this sum right here, this sum is going to have not one term in it, but two terms. But it's going to have an A1 and an A0 inside. But we know A0 and we know A1 in terms of A0. So what that will mean is that A2 will be entirely in terms of A1 and A0. So the upshot is if we continue, we get all of the AN in terms of A naught. And that's a justification for getting the Frobenius series y1 of x is equal to x to the R1 times 1 plus the sum from n equals 1 to infinity an R1 x to the n. And by an R1, what we mean is the coefficients that we got out of that formula when we plugged R1 in for R, which will just be some number that we know. So it's not an abstract thing. It's a solution to an equation. So it's actually a number. So that gives us the first solution. So that means that for any Frobenius situation, regardless of what the characteristic equation looks like, we always have one solution. There's going to be a split between the real and the complex cases, and we're going to have to look at the three cases separately because the behavior of the second solution is also going to deviate. So let's look at the three cases we talked about. In case 1, R1 and R2 were real and distinct. What does that mean? Well, it means that f of R2 plus n an is equal to minus the sum k equals 0 to n minus 1, pn minus k, k plus R2 plus qn minus k, ak is our recurrence relation. So the reason that we can't use this again if we have two copies of R1 is we don't get a second linearly independent solution. The problem is that if they're real and distinct, it's possible that I might hit an integer value. If R2 and R1 differ by an integer and I start adding integers to R2, I might actually hit R1 on the way somewhere. And then I'm just going to be right back where I started. Because that will mean that f of R1 plus n is equal to 0. So what do I mean again? What we did last time was we took this and we divided it on both sides. If R1 is equal to R2 plus some integer, remember R1 is larger, then what will happen is f of R2 plus n naught will be equal to f of R1, which will be 0. And I wouldn't have been allowed to divide by f of R2 plus n for every value of n. As long as that doesn't happen, I can do the same thing again. If not, then I could write down an is equal to minus the sum from k equals 0 to n minus 1, pn minus k, k plus R2, plus qn minus k, ak, all divided by f of R2 plus n. And this will be defined for n equals 1, 2, and so on. And again, now I've got Frobenius series coefficients in terms of the R2. So if they don't differ by a constant, if they're real and distinct and they don't differ by a constant, then we can build the recurrence relation in the way that we are used to, and we're going to get a second linearly independent solution that looks like this. y2 of x is equal to x to the r2 times 1 plus the sum from n equals 1 to infinity. Now an of r2 x to the n. That is to say, these are this family of coefficients that come out of that same recursion, but with r2 plugged in for r. So as long as they don't differ by a constant, f will never turn into a 0, and that means we can divide. So what if they do differ by a constant? So let's suppose that it is the case that r1 is equal to r2 plus some integer n. So if we make this substitution, that is, if we make the substitution that r2 is equal to that r2 is r1 minus capital N, and I take this and I put it over here, what I end up with is f of r1 plus n minus capital N is equal to all of this. Now I don't need to change the rest of it because I'm just trying to figure out where that f function turns into 0. Because what could happen is when n is equal to capital N, then this is equal to 0, and the left-hand side of all of this becomes 0. So when n is equal to n, you get 0 times an is equal to the sum from k equals 0 to capital N minus 1 p capital N minus k plus r2 q capital N minus k ak. So when we get to this point in the recursion, we've already going to have found a1, a2, a3, and every previous term up to an minus 1 in terms of a0. And what that means is that if I come up in here and I replace every one of these AKs with its same expression in terms of a0, all of this is just going to turn into a giant constant. So all of this, when I do all the grinding and computation out, there's no variables in there, it's just some number. And so what this expression ends up looking like, if you multiplied it all out and mash it all together, this says that 0 times an is equal to alpha times a0. If alpha happened to be equal to 0, if you combined all of these coefficients together and you ended up with an alpha that was equal to 0, then what that means is that an is arbitrary. And then you can just keep grinding the recurrence relation to figure out all the terms that come after it. So an is arbitrary, and you can determine all the rest. More generally, it's going to be the case that the alpha is non-zero. So what that means is that if alpha is not equal to 0, then 0 times an is equal to alpha times a naught is inconsistent. Because a naught is not 0. By assumption, we assume that a naught is not 0. So in that case, we actually have to use a different technique. And it's going to turn out to be the case that with a little bit of elbow grease, you can show that you have to use reduction of order on your original solution to get a second solution. So reduction of order is the tool in this case. And to remind you how that technique works, what you say is you assume that the second solution, y2 of x, is equal to some function v of x times the first solution. So this will be known, and it will be a Frobenius series. And what you do is you stick all that in there and you try to recover the v of x from the differential equation. So you assume y2 of x is equal to this, and then you plug in. If you turn the wheel on that, what you're going to end up with is that your second solution looks like y2 of x is equal to some constant a times y1 of x times the natural log of x plus the Frobenius series xr2, sum from n equals 0 to infinity of bn x to the n. So this is the general form if you have the case that you have an integer difference between r1 and r2. So if you do this computation, if there's an integer difference and you do this computation at the point where that recursion stops, and it turns out to be the case that all of those coefficients add up to 0, then you can just write down a regular old Frobenius series, because you can keep grinding on the recursion and you get a form that looks like this. So what do we mean? We mean in this case y2 of x is just equal to the regular old x to the r, n is equal to 0 to infinity bn x to the n. If r1 and r2 differ by an integer and the alpha coefficient that you calculate is not equal to 0, then the solution has this somewhat nastier form, your second solution, that you have to get out of reduction of order. What happens in case 2? Well, in case 2, you're never going to get a second linearly independent Frobenius solution from the recursion, because you can't plug in r1 and r2 into the same function and expect to get different results. In that case, you again use reduction of order. Remember, reduction of order was actually how we discovered that when you had repeated roots in the characteristic equation, in the constant coefficient equations, that you had to take your solutions and multiply them by x to get linearly independent solutions. Same thing here. y2 of x in this case, after you do reduction of order, is going to turn out to be y1 of x times the natural log of x plus x to the r1 sum from n equals 1 to infinity of bn x to the n. And this will converge at least on the same region that the original analytic functions converge on. Now, the reason I'm not working through these is because these derivations with reduction of order tend to be very long. But the idea is, once you make the assumption that y2 of x is equal to v of x times y1 of x, this is where the Frobenius series comes from, right? The fact that you have this y1 of x floating around in the assumption of the form of the solution means that you're going to get a new Frobenius series. Case 3 is where we have complex conjugates as roots to the index equation. And in that case, we can actually still produce a Frobenius series. It's completely happy to compute on a complex number. So it's going to turn out to be the case that when you do that, you write down y1 of x is equal to x to the r1 times the sum from n equals 0 to infinity of an x to the n. What will happen in this case is that these numbers will be complex. But the basic idea here is that because those roots are complex, that you can always take the form that you've got here, and it's going to turn out to be the case that y1 of x actually has both linearly independent solutions living inside of it. After all, we're interested in real valued solutions to the differential equation, not complex valued solutions. It's going to turn out to be the case that the real part of y1 and the imaginary part of y1 are both real valued linearly independent solutions. And there's a quick way to compute real and imaginary parts in theory. So at least in theory, we can always find one solution using the complex R1 and then plug it in and split it into the part that is real and the part that is imaginary. And both of those will correspond to linearly independent solutions. And so that's the whole story. There's really 3 cases to consider and a couple of subcases. And essentially it looks like this. So the upshot of all of it is this theorem. What the theorem says is, assume that you're working with x squared y prime prime plus x p of x y prime plus q of x y is equal to 0. And this is analytic at 0. P and q analytic at x is equal to 0. And assume that p of x is equal to the sum from n equals 0 to infinity of pn x to the n, and that q of x is equal to the sum from n equals 0 to infinity of qn x to the n. And let r1 and r2 be the roots of the indicial equation, r times r minus 1 plus p naught r plus q naught is equal to 0. Then we have 3 cases. Case 1, r1 minus r2 not an integer. Then y1 of x is equal to x to the r1, 0 to infinity of an x to the n, and y2 of x is x to the r2, sum from n equals 0 to infinity bn x to the n, where we can find those coefficients using the recursion relation. Case 2. R1 equals R2, which is equal to R. The first solution is the same, and the second solution is derived from reduction of order. What could happen in step 3 is that R1 minus R2 is a positive integer, and in that case, we end up with y1 of x is x to the R1 sum n equals 0 to infinity, an x to the n, and y2 of x is the even nastier, a y1 of x natural log of x plus x to the R2 sum of a second Frobenius series. All of the coefficients that are unknown here can be found by plugging directly into the recursion or the differential equation. We're not going to deal with complex roots in this setting. We are going to see them in Fourier series, but they're for a different purpose. So we haven't actually even finished a full proof of this theorem, mostly because it's very long-winded. It takes a lot of grinding to work through the symbolic computations. If you're interested in looking at the full details, in the appendix to the Good and Annan textbook, you can find a complete description of how all the steps work. But the upshot of all of this is, when you're working with Frobenius series, you want to look at the roots of the indicial equation, and then you're going to look at the relationship between R1 and R2. And these three cases completely describe what happens when R1 and R2 are real. Okay, so if you've got this far and you waded through this technical stuff, then congratulations. I'll do some example computations in the OneNote book. And for those 2 or 3 of you that watch this, thanks for listening.